Last time we were talking about NP, and I just gotten started on NP-completeness. I think I just ended giving the definition of what it was to be NP-complete. So a problem Y, or a language. And after class last time, I looked back at the book, and it's kind of funny that they do drift over into the whole notation that talks about problems as sets. Yeah, but they never use explicitly the word language. They keep talking, so they continue to talk about a problem, and yet they refer to it as a set. So they'll talk about whether Y is contained in capital Y, which means, as I've defined last time, whether input Y to problem capital Y has a yes answer, whether the answer to that question, problem Y, capital Y with input little y, is yes. In that case, Y is contained in Y. But as far as I could tell, they never defined that. So maybe I'm wrong. If somebody sees it in the book where they explain what this notation means, let me know. So at any rate, that's from the view of problems as languages. So a language Y is NP-complete if and only if two things. First of all, that language or problem has to be an NP. And last time, we spent most of the lecture defining rigorously or formally what it means to be an NP, which means informally that for any instance of problem Y, if you have a proposed solution, there's an algorithm that runs in polynomial time that can look at that proposed solution and decide whether that's a real solution. But, as I said last time, that's not a formally correct definition, and that's why we did the whole certifier and certificate definition. Okay, but the most important part of this definition is that for any other language X that's contained in NP, X reduces in polynomial time to Y. So what this really means is that Y is very expressive. It's a problem or a language such that it can represent any other language that's in NP. So if you want to solve, so what this means, you have a problem, well, I'll call it problem X, and all you know about it is that it's in NP, okay? Then you can solve it using a black box for problem Y. And moreover, that reduction happens in polynomial time. So in comes an instance of problem X, okay, and you're interested in solving that instance of problem X. So you want to know, is X contained in capital X, okay? And but instead of solving that directly, what you do is you do the polynomial time reduction to Y, which means this is an algorithm here which takes in little x, works on it in polynomial time, and produces an instance little y. So it produces a little y, which can be fed into the black box for problem capital Y, and then here out of here comes either a yes or a no. Okay? So any problem in NP, for any problem in NP, this is possible. So this problem Y, as I said earlier, is very expressive. It allows you to, any other problem in NP can be re-expressed as a problem in Y. Okay? And that re-expression only takes polynomial time. It's through this polynomial time reduction. So that's sort of the origin of the word complete. I don't know, you can invent other words for it, but that's where the word complete came from. These problems, an NP-complete problem is called complete for NP, complete for the class NP. Okay, so this is just, so far, just words, but we're getting closer to something that's of some use. All right, we know what NP is, what the reductions are. Now this is definition of NP-completeness. And previously we saw that P is contained in NP. Okay, that was we proved that last time. It's a two-line proof if you have the right definitions, which is what we did last time, set up the right definitions. Okay, now given that and given this notation for NP-completeness, we can sort of get some other results, maybe call them corollaries. If any NP-complete problem NP-complete problem or language is in P, then NP is contained in P. And since we know the opposite, that means P equals NP. Okay? So, how do we know that? This is also basically a one-line proof. It's just a use of the of this definition of what NP-completeness is. Okay? So, let's suppose some problem Y, which is an NP, is also in P. I'm sorry, NP-complete. So Y is an NP-complete problem, but it's also in P. Okay, so think of vertex cover. Okay, well, I didn't tell you vertex cover is NP-complete yet. In fact, I haven't told you any problems are NP-complete. But, so imagine an abstract problem Y, which is NP-complete, and imagine that it's in P, which means that there's a polynomial time solver for that problem. Then we're saying that NP is contained in P. Every problem that's in NP has a polynomial time solver. Well, what's the proof of that? Well, any problem, for example, problem X or language X, that's an NP, can be reduced in polynomial time to problem Y or language Y. That's what it means for Y to be NP-complete. And if it happens that Y is in P, that means that in this black box, we have a polynomial time algorithm that can always answer this question. Is this instance little y in capital Y? Okay. The assumption that capital Y is in P means there's a polynomial time algorithm for answering this question. So how do you then show that problem X there's a polynomial time algorithm for solving problem X? Yeah.
You reduce y to x, and then if y is also in P, you can reduce x to y, and use y to solve it, and then solve x.
Exactly, yeah. You reduce x to y in this case. Okay? So any instance of x, here it is, is reduced in polynomial time to y, and then you use the polynomial time algorithm here to solve that instance, and you get a yes or no. And of course, you do have to pay attention to how this reduction works. Does a yes here mean a yes here, or does a yes mean a no? But that's a detail of the reduction, and so I probably should have had something here which said interpret the yes or no appropriately. But this is a polynomial followed by a polynomial, and we've discussed this 2 times, that a polynomial of a polynomial is still a polynomial. So the polynomial time for solving problem x would depend on what's the polynomial for this reduction and what's the polynomial for this solver. But no matter what those 2 polynomials are, the polynomial of a polynomial, which would give you the polynomial time for x, is still a polynomial. Therefore, x would be in capital P also. So any problem in NP would be in P, which would then mean we have this equality because we already know the other side. Okay? So a corollary of this is that if there is any problem in NP that can't be solved in polynomial time, then what? Okay, P is not equal to NP. That's one thing you can say. P is not equal to NP. Okay. You can get another thing out of this, which is who said that? Yeah. Yeah, right. And no NP-complete problem can be solved in polynomial time. Okay, so that's another. Actually, this, I don't know if it's really right to call this a corollary. It's more like just a restatement, the contrapositive of this one. They're really the same, sort of the same thing. Well, I'll call it a corollary. It's an additional thing that we can point out here. Okay. But this is actually the one that's the most important, probably. No NP-complete problem can be solved in polynomial time. Okay? So we have these 2 consequences of basically the definition of NP-completeness and the definition of NP. And it's all very nice, but so far it's words. Why? What's missing in this whole theory so far, from what I've told you? We have a definition of NP. We have a definition of P, and we know problems are there. We know of some problems that are in P. We have a definition of NP, and we definitely know problems that are in NP. And now we have a definition of NP-complete, and we have some consequences from that definition of NP-complete. Do you know any problems that are NP-complete? Okay, so far I haven't said there are actually any problems that are NP-complete. We just have this nice definition. In fact, SAT, independent set, vertex cover, I think those are the only 3 that we've looked at so far, are all NP-complete problems. Complete problems or languages. Actually, 3 set we've looked at, right? Okay, so we've actually seen 4 problems or languages that are known to be NP-complete. Now, how do I prove that any one of these is NP-complete? All we have so far is the definition. The definition says that any problem, to be NP-complete, it means that any problem in NP has to reduce in polynomial time to it. So problem Y is NP-complete if and only if these 2 conditions. And the hard part is that is showing that any problem in NP is reducible in polynomial time to that problem Y. Being an NP by itself, that's no great distinction. I mean, being in P is usually, it's a good thing and often a hard thing for us to show. And it's an accomplishment when people have an algorithm that shows that a problem is in P. But showing that a problem is in NP is a pretty simple matter usually. Usually. Primality is the one notable exception. But showing that it's NP-complete, showing that this is true, is the first time difficult. And we're not going to do that in this class. So historically, SAT was the first problem that was shown to be NP-complete. And I don't know whether they do the proof in 120, but that's the class that, if they did it anywhere in the undergraduate curriculum, that would be where that proof would be shown. It's actually not that difficult. I mean, it's very difficult to find. I don't mean to in any way reduce the significance of when it was discovered in 1973 or so, but 72. But today, or even then, it was not that difficult to understand the proof. It's just very, very tedious. In 120, you build up all the machinery about Turing machines and formal reductions and so on, and then you can prove that SAT is NP-complete. But the proof is very, very tiresome and tedious. And there are other proofs of other problems that are NP-complete from the definition itself. So there are other problems that have lent themselves nicely to fundamental proofs from just from the definition. But in a moment I'll show you how you prove additional problems are NP-complete. And that whole endeavor is something that you will be able to do and that is done frequently, commonly. Okay, this proof that SAT is NP-complete was proved by Cook. I think it's 1972. Steve Cook at Berkeley. Independently in the Soviet Union at the time, I think it's Levin is the name, is now in Boston, also proved, not SAT, but a different problem was NP-complete. So independently, there were 2 people who sort of came up with this idea of NP-completeness and then proved that there are actual problems that are NP-complete in just about the same time. Okay, so there are NP-complete problems. We have this implication. If there's any problem in NP that can't be solved in polynomial time, then P is not equal to NP, and no NP-complete problem can be solved in polynomial time. But let me write this another way, and maybe I've already really written this. If any NP-complete problem is in P, then P equals NP, or every problem in NP is in P. Okay? Well, it's here already. Okay? I'm just restating it because it's really the most important thing. Because, again, being in P means there's an algorithm that actually solves the problem. It takes in any instance and says yes or no, and it runs in polynomial time. Being an NP only means that there's, again, informally, I'm not going to give you the full formal definition of a certifier, but it intuitively just means that if you give it the right answer, there's a polynomial time algorithm that can check it and say, yeah, that is the right answer, okay, and doesn't get fooled. And that's not a huge distinction. Every problem, with the exception of primality, pretty much every problem that we can think of is an NP. Okay, they're not all an NP, but and primality is an NP. But that why did I pull it out as an exception is because showing it's an NP is more difficult. But generally, every problem that we can think of, or you and I can think of, or will think of, is in NP, and we can show it rather trivially to be an NP, such as vertex cover, where the proposed solution is just a subset of vertices, and the polynomial time algorithm is just looking at them, and it's a trivial check. So being an NP is no great distinction. You know, it's like in the Cracker Jacks box. You know, at the bottom you get this little plastic pilot's wing. You know, whatever it is, doesn't make you a real pilot. Okay, all right. So being an NP is no big deal. All right, being in P is the real thing. And what this says is that if any one of these NP-complete problems can be solved in polynomial time, then P equals NP. Every problem in NP is in P. So that in order to know that a problem can be solved, actually solved with a yes or no solver or decider, that can be solved in polynomial time, it would be enough just to know that proposed solutions could be checked in polynomial time. The checking is so much easier than solving that the idea that the mere fact that checking is polynomial, could be done in polynomial time, would mean that solving could be done in polynomial time, that's just too strong to believe. Okay. So this says, this theorem, and this is a theorem, leads to the belief that no NP-complete problem can be solved in polynomial time. Okay? So most of this class has been about showing you algorithms that are efficient, problems that have efficient solutions. And what we avoided were all those problems that we don't have a efficient solution for. And now at the end, when we only have a week left and you can't demand your money back, we're saying, well, all those pretty problems that we can solve nicely, that's very impressive, but most of those problems out there we don't have efficient algorithms for, and we don't think we ever will. Because most of those problems out there are NP-complete, and this theorem leads to the belief that no NP-complete problem can be solved in polynomial time. So if you have a problem that you're dealing with, and you try to show that it's solvable in polynomial time, but you fail, maybe then you should try to show that it's NP-complete, because if you show that it's NP-complete, that gives some, puts you in the company of people who believe that no NP-complete problem can be solved in polynomial time. Okay, so what you're supposed to get from this class is an understanding of the logic of how this whole business comes about. The one missing piece in that logic is you haven't actually been shown that any NP-complete problem exists. Okay? But the rest of the logic is all here in the definitions. And this sort of, well, this is a belief, so it rests on your intuition, and you don't have to believe it. You may believe the opposite. So what's the evidence that no NP-complete problem can be solved in polynomial time? Well, first of all was what I just said. It just seems that if P equals NP, this says that if any NP-complete problem can be solved in polynomial time, then P equals NP. That means that any problem in NP would also be in P. And being in NP is such a weak property, and being in P is such a strong property, that just doesn't seem believable that NP would be contained in P. And the second piece of evidence is that people have tried a massive amount of effort has gone in to come up with polynomial time algorithms for problems that are NP-complete, and everybody has failed. But it's even stronger than that, okay? So let's say you spend a lot of time trying to find a polynomial time algorithm for SAT, okay, and you fail. And I spend a lot of time trying to find a polynomial time algorithm for vertex cover, and I fail on that, all right? Now, at first you may say, well, that's two separate efforts. You were looking at SAT and I was looking at vertex cover, and we both fail, but, you know, is that a combined effort evidence that P is not equal to NP? Is it evidence that there's no, maybe this is evidence that your failure is evidence that there's no polynomial time algorithm for SAT, and my failure is evidence that there's no polynomial time algorithm for vertex cover, but is the combined effort somehow evidence that P is not equal to NP? Anybody have an answer? Yeah.
Yes, because you can reduce one to the other.
Right. Because every NP-complete problem is an NP, and any problem in NP is reducible to into an NP-complete problem. Okay. If you have a polynomial time algorithm for one NP-complete problem, you have a polynomial time algorithm for all NP-complete problems. Okay? So when I was working on vertex cover, I thought, I'm just working on vertex cover, but really I was working on SAT too. And when you were working on SAT, you might have thought you were just working on SAT, but you were also working on vertex cover. So every effort to try to find a polynomial time algorithm for a particular NP-complete problem is really an effort to find a polynomial time algorithm for all NP-complete problems. Okay? And constructively, not just non-constructively, because because every problem in NP is reducible via real reduction here to an NP-complete problem. So if I'm working on vertex cover and I find that I have a polynomial time algorithm for it, through this reduction of SAT to vertex cover, I now have a polynomial time algorithm for SAT. Okay? So I wasn't just working on vertex cover, I was working on SAT also, and every other problem in NP, which means every other NP-complete problem. So I'm writing down the same things over and again, the theorem, the corollary, the restatement of the theorem. Somewhere else I might have written it. And I'll write it again in some other slightly different language. So either every NP-complete problem can be solved in polynomial time, or none can. Okay? And so all of the combined efforts that people have made over the years, even before the theory of NP-completeness, to try to give a polynomial time algorithm for some NP-complete problem, and their failure to do so provides the evidence scientific evidence, not mathematical evidence, that fuels the belief that no NP-complete problem can be solved in polynomial time. Now, there actually are people who think that maybe P is equal to NP, all right? But most people are not betting that way. Most people are betting that P is not equal to NP. And anyway, the failure up to now of anybody to get a polynomial time algorithm for an NP-complete problem is what fuels this belief. And that evidence continues. I mean, today, if you have a problem that you want to solve and you know it's NP-complete, you probably aren't going to invest a lot of time looking for a polynomial time algorithm. So that, in that sense, the evidence is not accumulating. But there are still problems where we don't know if it's NP-complete or not, and people try to solve it, show that it's in P, and fail, and then somebody, maybe them, shows that it's NP-complete. So their effort, until the point where it was known to be NP-complete, their effort to find a fast algorithm adds to that evidence. Okay. I can see people, yeah.
Are there any languages that are in NP that aren't in P that can't be polytime reduced to another NP language?
Let me parse that. Problems in NP
That is not in P that can't be polytime reduced to another NP problem.
Okay, problems in NP that are not in P. Well, we don't even know any of those. Okay? Here we have P is contained in NP, okay? And we have this whole business that would tell you something about when NP, which would imply that NP is contained in P, but we don't know whether P is equal to NP or not. We have all these implications, okay? So we don't know a problem, a language, which is in NP but not in P. If we knew that, then we would know that P is not equal to NP, right? So let me just emphasize that this question of is P equal to NP is P equal NP, that's unsolved. Okay? So we know some of the implications of whether P is equal to NP and whether P is not equal to NP, but we don't know whether P is equal to NP or not. Yeah?
If you were to make a wild guess, do you have any idea timeline for when you think this problem might be solved?
About 3 months ago. Yeah. Okay, the question was, when will the problem be solved? No, I have no personal idea, but about 3 months ago, maybe it was, there was a plausible proof that was offered. Plausible means it came from somebody reliable or believable, of P not equal to NP. They thought they came up with an actual proof. And since then, it's kind of fallen apart. I didn't even have the inclination or the tools to look at that proof. But the people who have, it's fallen apart, and the conclusion now is that that proof didn't go very far, didn't go anywhere. But it got a lot of attention. It was written up in the New York Times, and it's a lot of attention to that. So that's why I say 3 months ago, maybe it would have been solved P not equal to NP. Now, there are lots of people who come up with algorithms, and they're usually not from the computer science community or theoreticians or whatever, who come up with an algorithm where they insist this is a polynomial time algorithm for an NP-complete problem. And then they send it off to people in the field, and you get these emails periodically. And not very many people are willing to look closely at them. So who knows? Maybe somebody actually found the answer P equals NP, but nobody's willing to look at it closely enough to validate it. Okay. Because most of the people who are professional computer scientists are not putting much effort into trying to prove that P is equal to NP. If anybody's trying at all, they're trying to prove that P is not equal to NP. Okay, now in that the effort 3 months ago, and all of the excitement that was generated by that, there was a lot of online discussion, and there's a blog that was maintained by a very prominent theoretician Lipton, Richard Lipton. So if you look for it, you'll find a blog that he writes that has a long discussion of that excitement and a lot of other things in theory. And I was just told, I haven't read this line, but in the sort of summary of this whole issue of can you prove P equals NP or not equal NP and so on, he said, well, if we were invaded by space aliens and they insisted on knowing whether P equals NP or not, or they blow us up, if you think P is equal to NP, work really hard to try to prove it, save yourself by establishing that proof, that P is equal to NP. But if you believe that P is not equal to NP, proving that is so hard, the best thing you should do is to try to kill the aliens. Okay? Because he doesn't think that finding a proof of P not equal to NP is going to be easy. So, I don't know. There is a $1 million prize for anybody who resolves it one way or the other. It's the same $1 million that was, there are 8 or 10 open questions in mathematics that all have these $1 million prizes. And maybe last year you heard of one of them that was solved, and the guy who solved it refused to accept the $1 million. It was sort of a... Anyway, so it's on that same list. So if you resolve this, if you resolve that P is not equal to NP, you can collect your $1 million. If you resolve that P is equal to NP, you'd be foolish to take the $1 million, because if P is equal to NP and you know it and nobody else does, you can solve all these problems in polynomial time that everybody else is struggling with. And I'm sure that's worth vastly more than $1 million. Okay. So anyway, that's the status of the P not equal to NP problem. So it's still a problem. We don't know which way the answer is. But it makes a lot of good. There are a lot of logically interesting questions one can ask about this, and you may see some of them on the final exam. Or on your homework, okay? Because the last question on homework 8 was that in the book you have, in the book we're using, they ask whether or not independent set can be reduced in polynomial time to interval scheduling, okay? Well, independent set is NP-complete. Interval scheduling, we know, has a polynomial time solution. So they just innocently, I guess is the right word, innocently ask, can an NP-complete problem, this particular NP-complete problem, be reduced in polynomial time to this particular polynomial time problem that has a polynomial time solution? And I think what they meant as an answer was, well, I tried and I couldn't do it. But literally what they're asking, well, that's your homework question, is to, I guess I gave you a hint. Literally what they're asking is whether P is equal to NP. Okay, that question, that innocent-sounding question, is absolutely equivalent to asking whether P is equal to NP. And it's only problem 1b. They don't even make it just problem 1. It's just a sub-problem. So clearly they weren't really paying attention when they wrote it that way. And your homework question is to explain what I just said. Okay. Let me just point out one more thing about NP-completeness and P. Oh, I still haven't shown you how to prove the problems are NP-complete. That's really an important thing. Okay, I'll get to it in a minute. Okay, but what I was going to say is, here's NP. We know that P is inside NP. Okay, the P equals NP question is whether or not these two sets are equal or not. Okay, P is definitely contained in NP. And then there are these NP-complete problems. They're in NP also, okay? The only thing I can say about NP-complete, well, what can I say about this circle and this circle? They are disjoint, or who said disjoint? They are logically disjoint, or they are... Probably disjoint, or they are currently disjoint. Yeah, we don't know an intersection between these. That's definitely true. We don't know an intersection between these two, but we also don't know whether there is an intersection between these two. Okay, so I don't want to say they are disjoint, because that's talking about nature. And yeah, that's the belief. But all I can say for sure is that currently, at least in what's in the published literature, there's no known intersection. Okay. So this is sort of the empirical picture. And what you might hope is that the world looks like this. Well, you might hope that P equals NP. That would be great too. But if P is not equal to NP, then what you would hope is that what NP looks like is that you have problems in P and everything else is NP complete. Why is that a good thing? Because if P is not equal to NP. Why is that good? That's good because if you have a problem you're working on and you're trying to show a polynomial time solution to it and you fail, then you'd like to try to prove that it's NP complete and at least resolve why you failed. Or that you should, that's some evidence, strong evidence that you're never going to find a polynomial time solution, at least you can go on to some other problem. But the reality is that the world does not look like this. Nature does not look like this. It's known, this is a theorem, also proven early on in the 1970s, if P is not equal to NP, then there are problems, I'll call them problems, or languages, problems in NP, not in P or NP complete. So there's some set of problems in here that are neither in P or NP complete. And that means you could be very unlucky. The problem that you're trying to resolve, you can't show it's in P because it's not. You can't show it to be NP complete because it's not. And so you're just left with failure. You're just left not knowing. And that's very unsettling. There have been various candidates. This is a purely mathematical, non-constructive proof. I believe it's non-constructive. I even taught it once, but I can't remember. But my point is that there were some candidates of natural problems in this Netherland. And as far as I know, every one of them that people had conjectured or thought might be in there ultimately was resolved either to be an NP complete or resolved to be in P. So I don't know of any natural problems that are in here that are still, that are conjectured to be in here. But this is a theorem. Those problems do exist. They just may not be the ones we are interested in naturally. Okay, so what I haven't shown you is how do you prove that a problem is NP complete, given that we already know some problems are NP complete. So the proof initially that SAT was NP complete, the proof initially that whatever problem Levin used to show there's NP complete, those proofs were very, very, I mean, that discovery was very profound and creative. Although, as I said, the proof itself is just very tedious, and you can go through it. And I think it's done in 120. If not, it could be. Okay, so how do we, that is, how do you, or we show a new problem is NP complete? Okay. You have all the tools to answer this question. If I put this on a homework question, you should be able to come up with the answer. Okay? What do you have, first of all, to show that a problem is NP complete? You have what I erased. It used to be over here, which was the definition of what it means to be NP complete. So you have a problem, a new problem in hand, 4-sat. Okay? Not 3-sat, but 4-sat. that's rather trivial. But anyway, you have some problem, which I can describe, and you want to show that it's NP-complete. According to the definition, you have to do two things. What are those two things? Yeah.
Write an algorithm that can solve it, an instance of the problem with a certificate or a hint of what the solution would be?
Well, in other words, to show that the problem is an NP.
Yeah.
Yes, right. You want to show that it's an NP, which, as I said, is usually a fairly trivial thing because the hint is going to be a proposed solution, and the algorithm is really just checking it. Okay. So you have to show that it's an NP. But the second part is that, by the definition, how do you show a new problem, call it Y, is NP-complete? Definition, the second thing is for any x containing an NP, x reduces in polynomial time to Y. But you know some NP-complete problems, okay? So let's say you know, for example, that the SAT problem is NP-complete. And now you want to prove problem Y is NP-complete. So how can you prove that Y is NP-complete knowing that SAT is NP-complete? Yeah.
You want to try to reduce SAT to Y.
Yeah. Okay. It is sufficient to show SAT, a specific known NP-complete problem, it reduces in polynomial time to Y. Because we know that every problem in NP reduces in polynomial time to SAT. We know that because SAT is NP-complete. So if SAT reduces in polynomial time to Y, then by transitivity, by the fact that polynomials are polynomials are polynomials, every problem in NP reduces to Y. And constructively, you can do it by taking any arbitrary problem in NP, reduce it to SAT, and SAT reduced by the specific reduction you just came up with to Y means that for any problem in NP, there's a specific reduction to Y. So this is how you prove new problems are NP-complete. It's just the chain letter business. You just chain your new problem onto this chain of implications, chain of proofs of NP-completeness. Now, you don't have to go directly from SAT, because now there are tens of thousands of problems that are known to be NP-complete. When you have a new problem Y, you just use any one of those NP-complete problems and show how it reduces to Y. Yeah?
How did they show the first NP-complete problem?
I didn't. Crook and Levin did. Okay, and we didn't do it in this class. So what I'm saying is that the proof actually might be done in 120. I know when I taught 120, we did the proof. It's tedious and takes about a week to go through it. And not everybody chooses to do that. But yeah, I mean that's a central piece of the whole business, that there really are NP-complete problems. And once you have a nice library of them, when you want to prove a new one is NP-complete, you look through the library to find something that seems similar to Y, and that means that you'll probably be able to come up with a nice reduction. The reduction mechanism won't be that difficult. Although sometimes these are very clever. The details of doing the polynomial time reduction can be very clever. And early on in the 1970s, people would publish these. Today, now, it's not that publishable because they're a dime a dozen. But mostly the reductions are pretty trivial, pretty straightforward. If you find a problem in the known repertoire, the known library, that's pretty close to what you're wanting to do. And your homework asks you to prove something's NP-complete, I believe. That's one problem. Either that or it asks you to do a reduction, but then that's the hard part of it, doing an NP-completeness. Let me just say one more thing. The mistake that most people make, and this will be on the final exam, and some people will make this mistake, is when you want to prove a new problem Y is NP-complete, you reduce an established NP-complete problem to Y. That's the logic of it. You don't reduce the problem you're trying to prove as NP-complete to an established NP-complete problem. That does nothing. Okay? If this is an NP, which it has to be NP-complete, showing that it reduces in polynomial time to something that's NP-complete is completely unnecessary, and it's unproductive, but it's also unnecessary because we know that everything in NP reduces to an NP-complete problem. So even if you come up with a clever reduction, you haven't done anything. Okay? All right. One more class. See you on Friday.